Okay, Simon, thank you very much. And thank you very much for the invitation to speak this morning or this afternoon, as the case may be. I'm Hal Finkel. I hail from Argonne National Laboratory's Leadership Computing Facility, where I lead our compiler technology and programming languages team. I'm also the vice chair of the C++ Standards Committee and have been involved with standardization and work for C++ and from SICL. And I'm going to talk to you today about programming models, about compiler technology for Exascale, and about the intersection between the two, often in the context of the United States Department of Energy's Exascale computing project. So I want to start out before we really talk about programming models and compilers. I want to talk a little bit about application structure and development process. So when we talk about designing applications for modern HPC systems, the first thing I like to say is it's very important to have in mind the correct kind of development workflow that you're going to follow. So the traditional idea of how you develop scientific applications for HPC or any applications for HPC is often something like this. This is the cartoon that people have in mind. You start with a science problem, you analyze that problem, you choose some algorithms that you're going to use, you implement and test those algorithms. Then you go to optimize them. And when you optimize them, you take into account all of the relevant properties of the machines on which you're going to run and so on. And then in the end, you have this high performance code that you run. And the sad truth, perhaps, is, as you might imagine, that that doesn't actually work very well and works increasingly less well over time. So the important thing to realize is that the real workflow has to look something more like this. You have your science problem, and then you consider your target architectures. Now, the reason why you have to do this up front is because there are a lot of structural properties of your application that really can't be changed after the fact by compilers or even localized changes in programming models. And when you design your algorithms, you have to design them in such a way that they are parameterizable. We'll talk more about that. And able to be adapted to different kinds of programming environments. And as we look at how we design applications, there are these trade-offs between things like representations and regularization schemes, solver techniques, which degrees of freedom in your problem are computed versus evolved, and so on. These are choices that have to be made at a very high level. They can't be made by a compiler, and they really can't be affected by a lower level programming model choice. And so it's really important that your application design process considers these things in combination with properties of the architectures on which you're trying to run as you go through the workflow of designing your application. Now, does this mean that performance portability is impossible? No, but it does mean that performance portable applications tend to be highly parameterizable. It tends to be the case that there's no one good answer for those various algorithmic trade-offs as you move from the scientific problem domain into the algorithmic domain. And so you need to be able to select different options for those different trade-offs as you're targeting different machines, and even as you're targeting the same machine as you move between different problem regimes. There are also other changes or structural properties of an application which really need to be thought about up front, and they will affect scaling and performance, especially as we move to larger and larger machines. One property which comes up a lot is that the need to avoid central coordinators. And this idea that you're going to have one or only a few nodes that somehow hand out work to a bunch of other things just doesn't scale. In some sense, this goes without saying, and it may be the case that everyone who's actively on this call right now would know to avoid such a thing without thinking about it too much, but it does come up repeatedly as we consider application designs, and it's, I think, worth noting that these structural properties of applications are important. The other thing that comes up a lot is load balancing. So it's really important when you think about application design to think about how the computational load is going to be balanced across the various computing elements. And this is true all across the levels of parallelism and that are available on a system. It's true at the level of processing elements on a GPU or on an accelerator, and it's true on the level of nodes that are connected by an interconnect where you're using MPI. It's true across cores and sockets. The idea that you're going to have to distribute the workload in a way to effectively use these resources is something that a programming model can help with in some cases, but it really has to be something that's designed in structurally to the application. And only when you have all these kinds of structural properties taken care of, are you really going to be able to meaningfully exploit a programming model to its fullest and the compiler technology to its fullest in order to get good performance. The other thing that I think is useful to point out is that there's value here in following the crowd to some extent. So we often talk to potential users at the facility about application architectures and choices of various kinds of dependencies and so on. And in order to have dependencies that are supported across a large array of architectures and environments, that takes a lot of non-trivial development, and you need a large user community behind those things. And so it's important in some sense to think really hard before you take the road less traveled, as the saying goes. Okay, so now let's talk about programming models. Now, one thing that's really important to think about when you think about modern systems is that to effectively use them, you need parallelism. But you don't just need some parallelism, as you would think about in a traditional sense. You need a lot of parallelism. Modern GPUs can run tens of thousands of simultaneous threads, and or at least need that many schedulable in order to do latency hiding. And so it's really important to think structurally about how you're going to have your application expose that level of parallelism in order to make effective use of the resource. As we heard from Jed yesterday, and in other talks throughout this workshop, there are trade-offs here between throughput and latency. Often you need to have problems that have a sufficient throughput requirement in order to take advantage of this kind of parallelism. But it's very important to consider this. Other factors that need consideration are transition overheads. The data needs to be moved between different accelerators and the host, of course, between different nodes on a large-scale system. And there's a trade-off there between what you compute and where you compute it. We've often found that we execute tasks on accelerators such as GPUs, not because the GPU actually accelerates that particular task, but because moving the data back to the CPU would be more expensive than computing it on the GPU. And the third thing that is important to note is that, again, on this application structure point, you have to make sure that your algorithms and your application expose flexibility in your data placement and layout choices. It will not really be feasible to take a poorly structured application and change it to get good performance on modern architectures just by changing some loop structures in the code. And this is often the idea people have naively when they think about using accelerators is, well, they have these loops and they're just going to put some magic thing around their loop. And maybe it's tedious to do that. Maybe it's easy. but they feel that the change can be localized, and often the problem is the change really can't be localized in that sense. The data layout and placement is exceedingly important. Okay. Now that having been said, now let's talk about how you actually express parallelism and data movement in different programming models. And there are different programming models that are available across these different machines. Some of them are standardized programming models. Some of them are vendor-specific programming models. The one programming model that we need to consider is OpenMP. OpenMP is a programming model that's been used for many years to exploit host-level parallelism across cores on a CPU. And it has been extended now in order to support GPUs and other kinds of accelerators. So this is sort of well known. The way you use OpenMP is that you put pragmas in your source code, and it is a language extension that is understood by the compiler. It has support for both host-level parallelism, both in terms of data parallelism specifically, and also generalized concurrent execution with tasks. For example, it also supports accelerators, it supports data movement between accelerators, and it has specific support for SIMD execution as well. So there's a lot of flexibility there, and it comes in the form of these directives that you place in the source code. Another programming model, which is quite important for us, is SLE. And we have been doing a lot of work at Argonne with SLE and with Intel's current extensions to SLE called Data Parallel C++. This is an important programming model. It's designed to be a modern C++ programming model, and it's a standard from the Khronos group, which makes it very attractive from a cross-vendor support standpoint. Now, one thing I want you to notice here, and we'll come back to this later, is that the constructs in this programming model are sort of language and library based. So you create objects such as queues and buffers. You submit things to queues and access things through library abstractions. This is going to have certain trade-offs as we think about compiler optimizations later as a trade-off versus user control. The other thing that I really need to mention, it's a very important part of this space, are the parallel programming frameworks that are being developed. Here I'm highlighting two of them that are developed by the U.S. Department of Energy. One of them is called Raja, developed at Lawrence Livermore National Laboratory, and one of them is COCOS, which is developed across the DOE, although primarily at Sandia National Labs. And you can see here that they both provide sort of wrappers around parallel loops. They also provide many other features as well. But they're built around this idea that you can use modern C++ to abstract parallelism and target many different devices. Now, COCOS and Raja, for example, can both sit on top of OpenMP, but they can also sit on top of vendor programming models directly, such as CUDA or HIP, and or SLE, and as the case may be. And so you get this level of portability by using these models. The parallelism libraries can also be evolved more quickly than can standardized languages. And so that serves as an important way that we get implementation experience for the standardized approaches. The other thing that is really important to mention is that the way that you abstract parallelism is not just limited to adjusting loops. As I mentioned before, data layout and placement is exceedingly important. And one thing that's important to note about COCOS, but some of the other models as well, is they are developing support to deal with this particular aspect of the problem. So COCOS, for example, has a concept of views and memory traits and memory spaces that can, or execution spaces that can allow the user to adjust where memory is stored and how it's stored. So this graph here is old at this point. It's from 2013, but it goes to show you that choosing the correct memory layout can help considerably with performance. So here on a GPU, you can see that this is an older GPU, but in this particular case, placing memory that is constant but randomly accessed, for example, into texture cache, can provide a significant performance boost over the sort of naive mapping. Okay. The other thing is that all of these things are leading into changes into the C++ standard itself. So starting with C++ 17, the standard library adopted parallel algorithms. So with your standard algorithms, you can have parallelized and even vectorized execution of different algorithms. This works to varying degrees depending on the algorithm and the implementation in terms of performance. But the idea is that you have an ability to support parallelism. And the concepts from Cocos, from SLE and OpenMP and other sources dealing with execution spaces and affinity and placement and data movement are all being considered as proposals are being written to evolve the C++ standard in the future. So one thing I do like to point out, it's another important part of this space, is that we're seeing an increasing number of applications and libraries and frameworks that are using just-in-time compilation in order to adapt the code being executed on the architecture for the specific computation that has to be performed. This is commonplace now in machine learning frameworks, and it is something that has been used quite extensively in OpenCL implementations, for example. And we have applications that take advantage of this in both of these cases in order to get optimal performance on architectures by adapting themselves to their problem, to the architecture, to the problem domain dynamically. Now, it can be challenging to develop and use these kinds of technologies, but they can provide significant performance boosts. And we're seeing an increasing prevalence of frameworks and libraries that are using just-in-time compilation, whether it's Intel's library for small matrix multiplication, or Halide, or XLA, or OpenCL, and so on. And this prevalence of adaptation to the architecture, I think, will continue. In fact, we even have some users who have been investigating using Julia for programming, specifically because it provides just-in-time compilation capabilities as well. All right. Now I want to spend some time talking about compiler optimizations and our focus here. So one thing that I think is important to start out with is that our focus for Exascale compiler development, especially from the US Department of Energy side, has been around the LLVM compiler infrastructure. So let me take a few minutes and just explain what this is. The LLVM compiler infrastructure is an open source compiler infrastructure. So it's an open source set of libraries and tools that are used to create compilers and other toolchain components across a variety of different architectures. It's liberally licensed and can be incorporated in to vendor tools, as well as used in its direct open source form. Importantly, it has a very large and active user community, and it includes contributions from essentially every vendor that is relevant in the HPC space. So importantly, on this diagram, and I'm proud to say that all of the arrows between LLVM and the various vendors go in two directions. So all of these companies use LLVM for products that they ship, and also contribute back to LLVM. And that's in addition, of course, to companies that make substantial contributions to LLVM but are not traditional HPC companies, such as Apple and Google and Microsoft and so on. Plus, of course, we have contributions from academia and from the national labs as part of this effort and as part of other efforts. So LLVM is not a low-level virtual machine, as you may have heard the term was originally intended to mean. But it's an architecture that combines the ability to provide sort of architecture independent optimizations with architecture dependent optimizations and lowering into code for particular architectures. The most well-known producer of LLVM's intermediate representation is Clang, which is a C and C++ front end for LLVM. And Clang not only can do code generation, but it also has a sophisticated static analysis engine, which is being increasingly used to find bugs and otherwise check code before it is run. Okay. Now, the LLVM project has a number of different components. It has not only Clang and the sort of core LLVM libraries, but it also has LDB, which is a debugger. It has a C++ standard library. There's an OpenMP implementation and associated runtimes. There's a linker and so on. A couple of new additions, which definitely need to be mentioned. One is Flang, which is our new C++ front end. This is started as a collaboration between the United States Department of Energy and the PGI division of NVIDIA, and now actively involves ARM and participation from a number of other vendors. There's an older version of Flang, which is still actively maintained and is based on PGI's front end. This is a production quality Fortran compiler for CPUs, including OpenMP support. And there's also a new front end being written, which was called F18, which has now been merged into the LLVM project itself as Flang. And this is written in modern C++ and is under active development. This is LLVM's official Fortran front end. Another thing that you may have heard about is something called MLIR. This is also now part of the LLVM project. It started as an effort to improve the compiler technology inside of Google's TensorFlow project, which is a machine learning framework. And it is now used in LLVM in order to do high-level optimizations. And importantly, the Flang inside of the LLVM project uses MLIR. So Flang actually gets to take advantage of this infrastructure that was developed by Google for machine learning optimization in order to optimize Fortran code. And we have a number of what are called dialects in MLIR that are being developed, in addition to the base dialects from MLIR itself. So we have a dialect for representing OpenMP, for example, which is being used to support OpenMP in Flang. Over the years, we've added features into Clang and into LLVM that specifically are designed to address the needs of the HPC community. I like to highlight this one because many people have seen this already, even though they didn't realize they were seeing it. And that is that Clang has what are essentially MPI specific warnings. And so if you use a version of MPitch or OpenMPI that and you use Clang and you have a mismatch between your type tag and your provided pointer, it will warn you. This is actually not really MPI knowledge built into the compiler, but a set of attributes that were developed and added into the header files for MPitch and OpenMPI some years ago. We first deployed this at Argonne, but it's since been merged upstream, so everyone benefits. Another thing I point out quickly is that Clang is not only a C and C++ front end, but also compiles CUDA code. And this capability has been adapted by AMD as part of their HIP programming model. Okay, but LLVM supports GPUs from a number of different vendors. There's the NVIDIA support, which has been present for quite a while, as well as support for AMD GPUs, also present for quite a while. And we also have a path to support Intel GPUs through the Kronos SPIR-V translation layer. All right. I want to just spend a couple of minutes talking about how compilers optimize code and the trade-offs there. So one thing that we think about as we think about choices of programming models is the trade-off between programmer control and compiler optimization. So we would like it to be the case that you can select a programming model and then the programmer can write optimal code for their target architectures using that programming model, with the key there being on the plural of architectures. Now, the problem, of course, is that there may not be one way to structure the code to be optimal across all these different architectures. And there are also other constraints on the way that users write code. There are software engineering concerns, and there are abstraction layers. There are divisions between teams who are writing different libraries and so on. And so it may not be possible for the code to have the optimal structure for execution on a particular architecture. And so one of the things that we've been working on is compiler technology that can remove some of these abstraction penalties and allow the compiler to use its knowledge of the targeted architecture in order to optimize the parallel constructs inside of code. And you can see here there are various options. So for instance, one thing that might happen is a compiler might want to combine or split loops inside of parallel regions or the parallel regions themselves. And one thing that is important to point out is that when you start giving the compiler knowledge of the programming model and ability to optimize, this can have a significant effect on performance. One thing that is unfortunately true is that if you take a serial application and you run it, and then you introduce a parallel programming model, but then run that parallelized version with only one thread of execution, your performance is often worse than the serial version. And you can make up for that by scaling, but of course, that deficit stays with you. And one thing that we hope to be able to accomplish with better compiler technology is to remove that kind of penalty. And here is a quick example of some work that we did a couple of years ago that demonstrates that we can do that in many cases. But it requires the compiler to have knowledge of the programming model. So here, let me just quickly highlight some considerations here for different programming models. So here we have OpenMP, we have DPC++ and SLE, and we have Cocos and Raja. Now, one thing that is important to realize is that the compiler has different levels of visibility into these different models, and for things like Cocos and Raja, it depends greatly on what the underlying kind of backend layer is. So the compiler optimization potential for OpenMP, for instance, seems to be higher than for SLE because the constructs are more directly visible to the compiler for OpenMP. With SLE, the compiler would have to understand the structure of queues and the dispatch that is associated with that. Whereas with OpenMP, the constructs are much more directly embedded in the control flow of the program. Now, if you're using Cocos or Raja, it's really then going to depend on which backend you're using. Those libraries can also introduce other abstractions that can be hard for the compiler to understand, but on the other hand, have advantages in performance portability. And also give you a greater ability to parameterize your code. As I mentioned at the beginning, parameterization of code is exceedingly important. OpenMP has a deficit in that regard because pragmas tend to be directly embedded in the program, and some of these pragmas cannot really be abstracted, such as reductions, or at least some of the clauses can't be abstracted. But if you have a modern C++-based framework, such as SLE or Cocos, then your ability to have a parameterized code that you can adapt is much higher. And the last consideration to point out is that with Cocos, for example, you have much better support over data layout and placement. Now, looking to the future, one thing we have to think about is the possibility of sending data sort of more directly between different accelerators, as opposed to having a host to accelerator dispatch model. And none of the frameworks really handle that well yet. So I think that's just a point for future consideration. So am I out of time at this point? Let's see. I don't hear what you're saying, but I'll just quickly say that LLVM is a large open source project. And one of the things that we have definitely noted with open source projects is that there is this trade-off that's important to note. So if everyone contributes to a project and everyone contributes to the general upkeep of the project, then then the project can be healthy and can be used to support a really healthy ecosystem. But that requires investment in that base infrastructure. And one of the things that is important about the ECP effort in the United States and similar efforts is the way that they can contribute to the base infrastructure of these various projects that are used across the ecosystem, and therefore help keep the whole ecosystem healthy and productive for everybody. And this requires, you can look at the slides later, that we have a good amount of contribution from various parties, including and very importantly, making sure that code gets reviewed in a timely fashion across large organizations with large product, many contributors. This is a particular challenge. All right. So with that, let me conclude. We have so one thing is, as I mentioned at the beginning, applications around libraries really need to be designed to be scalable and performance portable from the beginning. This is a structural property of the applications that is important design up front. Second is there'll be a variety of programming models that are available. And there's a trade-off between the composability optimized, between user control, and the ability to adapt to different problem domains and architectures at runtime. And the third thing is that the LLVM compiler infrastructure is really a key part of our programming environment across all of HPC, and that it's a large project and requires care and investment to keep it healthy.
Brilliant. Thank you very much, Hal. I think you've given us some really great tips and pointers there for the UK Exascale initiative. So thank you very much. Really appreciate it, and know it's an early start for you as well.